being there for this second lecture. So today, after the presentation of what is Bose-Einstein condensation, why BCs are superfluids, and what are the collective modes, I will present you the way to develop trapping potentials for atoms, which can have shapes quite different from usual shapes that you have with optical or magnetic traps, thanks to the use of adiabatic potentials. Okay, so this is the same list as what I showed you the first day for the benefits of quantum gases and why they can be useful, for example, in the context of quantum simulation. And today, I will, especially with this trap, show you potentials which will allow the dynamical control of the confinement geometry, but can also let you control the temperature of the sample, the interaction strength, essentially not with special resonances, but by the control over the transverse confinement. The possibility, even if I will not use it tomorrow, to have periodic potentials or at least double wells, triple wells, using several RF frequencies, and the accessibility of low-dimensional systems with these traps. Okay, so the general overview of my presentation is as follows. I will first introduce you with the principle of adiabatic potentials, then give you a few examples, and then the probe tools we have to characterize the potentials. If you need references, there are two recent reviews that I wrote with my colleague Barry Garraway from Sussex University. This one is a published version of lecture notes I have given in Les Ouches in 2013, so it's more pedagogical in the sense that all the calculations are presented, you will find all the details. And this one is more a review on the different traps that have been done, and so an overview of the landscape of people using these potentials. Right, so let's start with the principle of adiabatic potentials. And then general idea is that you have a system with eigenstates, quantized eigenstates, which depend on some parameter, lambda, which is kind of an external parameter. So these states have eigenenergies, h bar, omega, of this parameter. The splitting between energies is delta of this parameter, etc. And this parameter can be typically, in the case I will describe, a magnetic field or a radio frequency or any external parameter. So this parameter can vary either with time or position, and we wonder, are these eigenstates that we computed for a given value of this parameter still relevant if we vary this parameter or not? And this is true, that they are still relevant for slow enough variations of this parameter lambda. So this is a theory of adiabaticity. If the parameter lambda varies slowly with time, such that its variation are small as compared to the splitting, the frequency splitting between states, so essentially this lambda dot should be smaller than the splitting, or in an equivalent way if its spatial variations are small enough, so spatial variation can be recast into time variation. If the atom moves with some velocity, so its velocity times the spatial variation is equivalent to a time variation of the parameter. And again, this has to be small as compared to the splitting between levels. So if this is slow enough, the atoms will nicely follow the local eigenstates given by the local value of the parameter lambda. If the variation is too fast, for example, if the atoms moves too fast, or if I make a scan of the parameter lambda with time too fast, then there may be lambda Zener transitions, non-adiabatic transitions, between these states and this one, for example. And this will occur especially where the distance between the adiabatic states is the smallest. So at this position or at this position, I have a highest probability to change the eigenlevel. And if this black state consists in a trap for the atoms will be lost. So for example, here, I look at this specific position. Imagine lambda is linear with position. So now my lambda is just a position. This point here, if I have a potential which is minimum at some position, it's a trap. So this constitutes a trap for atoms as long as the atomic motion inside this trap is not too fast. Otherwise, it may decay to this state, which is not a trap, and be lost. So the general idea is that we will try to trap atoms in such minima of an adiabatic potential. Okay, so the potential I will present you and the adiabatic states are magnetic states. Magnetic states because the radio frequency coupling, which I will introduce, couples, it's very low frequency, so the main coupling term in this case is the magnetic coupling, dipolar coupling, and not the electric dipolar coupling, which is dominant at larger frequencies. So from low radio frequency means between, let's say, a few tens of kilohertz to a few tens of megahertz in the case I will discuss here. But this is also true for hyperfine coupling, which are in the gigahertz regime. That's the magnetic coupling which is relevant. So I have to consider magnetic states, and I have for this to consider spin operators, or more generally, because there may be also a contribution of the electron orbital angular momentum to the total angular momentum operator, which is the one which is relevant for the atoms. So this total angular momentum operator F, I have not wrote it again, but I can do that. It is the sum of J plus I, where J is the sum of L plus S. And what are all those stuff? So you have an atom with a nucleus and an electron. And S is the electronic spin. L describes the orbital angular momentum of the electron. And I is the nuclear spin. So with moderate magnetic fields, the relevant angular total angular momentum is F, and MF is a good quantum number to describe the eigenstates. At large magnetic fields, then it will be the electronic spin which dominates, and you would have essentially two spin states, plus and minus 1/2 for the electron. So this is a Paschen-Bar graph. I have not shown it, but essentially I will stay with low magnetic fields. So F is a good quantum operator, and MFs are good quantum numbers. So I will just label them just M. Remember, it's MF. So there are bases in which F squared and Fz can be diagonalized simultaneously. The eigenstates are labeled with M in the direction Z set by the choice of the quantization axis. And the eigenvalues are FF plus 1 H bar squared for F squared and MH bar for Fz. You can build all the M states by using the F plus and F minus operators, which are given as a function of the projection of the total spin around X and Y, and applying, for example, from the lowest minus M equals, M equals minus F state, the F plus operator, and from that you go from minus F plus 1, minus F plus 2, blah, 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 up to plus F. Yes, question? well, first, here, in fact, L is 0. But still, no, it couples also to F, in fact, to F totally. Well, yeah, that's true, that you really have the total M state with M eigenstate of F, which is important at low magnetic fields, not only. Yeah, but when you are in an excited state, where L can be 1, for example, in a P3½ state. Yeah, this is all describing all that. This is a hyperfine, well, they are couplings, okay? So the hyperfine, this is a hyperfine eigenstate because in fact there is a hyperfine coupling. So the true eigenstates are not the eigenstate of I or S anymore. That's combinations of them. And here there is a fine structure coupling which shifts degeneracy. But that's true for L being equal to 1, not in the ground state. I speak too much. Okay. So we have our eigenstates, which are there for any quantized direction of the magnetic field. So I just remark now that Fx is also the half sum of F plus and F minus, because I will use it in a moment. Now, when there is, to start with, a uniform static magnetic field, it splits the degeneracy between all these magnetic substates. And the Hamiltonian of the interaction between the spin and the magnetic field is minus gamma F dot B. So that you can also introduce the Larmor frequency, which is omega naught being proportional to the magnetic field. And so the Hamiltonian, in fact, you can just write it as being a frequency times just a F operator. And the direction of this F operator is set by the direction of the magnetic field, which gives you the quantization axis. And then the eigenstates are just equally spaced by h bar omega along this axis, which is written just here. Okay. Now, imagine that B0, our static magnetic field, depends on position. So now position plays the role, or B of R plays the role of my parameter lambda I introduced initially. This means that at any point R, I can perform this spin diagonalization and find the eigenstate at position R, which are M for the direction U of R. Because I can also write the Hamiltonian as being a F taken in the direction, in the projection U of R. So then, if everything goes slowly and the atom can follow adiabatically the direction of the magnetic field, the energy of this eigenstate set by the direction of the magnetic field is, as before, just m h bar omega 0 local. And so that means that this energy can act as a trapping potential, as I explained in the first slide. And the trapping potential is just proportional to the modulus of the magnetic field. So why the modulus? Because we have said that we are going to take as a quantization axis the direction of the magnetic field. So we already are in the proper direction, and thus the splitting between states is proportional to the modulus of the magnetic field. And this is simply our potential energy we will use to trap atoms in magnetic traps. And so if we choose properly, so I forgot a little m, which should be in front of this formula. If you choose properly the magnetic state such that it has a relevant orientation with respect to the magnetic field, this potential is positive, and then the atoms will be attracted to positions where the potential the magnetic field is minimum. So they are called low field seekers in the sense that they reach for the minimum of the magnetic field. High field seekers are not used because you cannot produce, in fact, a local maximum of the magnetic field. That's forbidden by Maxwell equations. Okay, so some examples of magnetic fields. A very simple one, two coils with opposite currents. They create a quadrupolar field. At the center, the field is 0, so you cannot do better for a minimum, and 0. So the atoms will be attracted to this 0 of magnetic field. The magnetic field has this expression. It's linear along any of those lines. Otherwise, its modulus, which is a relevant trapping potential, has this shape with a square root. So the fact that the field is minimum, well, that the minimum is 0 in the center may cause problems with my assumption of adiabaticity, because as I said initially, I need that this distance delta is large as compared to the way the parameter lambda varies. But now, if this distance is 0, the splitting is 0, it cannot be large as compared to anything. So any small velocity the atoms will have if they go through the 0 to the center of this magnetic trap, they will be lost. They will make a spin flip. So what people do is either you have particles hot enough such that they have an energy and they avoid the center statistically. So only very little atoms are lost because the density in the center is quite low. Or you play tricks like moving the 0 to avoid, for the atoms to avoid it. That's called the top trap, and that's a trap which was used for the first realization of Bose-Einstein condensation. Or you plug the 0 with a laser, like that. Oops, sorry. Like that. So the atoms cannot go where the laser is. And that's the trap which was used for the second BC in the experiment of Wolfgang Ketterle. But you have to take care of these non-adiabatic losses at the center, yes. So what will happen then? Exercise. So this is a form of the magnetic field. Now you say, okay, just add a constant magnetic field along Z. So what will happen? Don't look at this formula and add an offset of magnetic field with a direction along Z, for example. Okay, so I will have, let me just look along, so that I will have B prime x ex plus B prime y ey, and then minus 2 B prime z ez, and then I add something, B offset, well, B1 ez. But now I define Z0 as being B1 over 2B prime. And then I can write that B prime x ex plus y ey minus 2 z minus z0 ez. So a quadrupole plus a homogeneous magnetic field is just the same quadrupole, but displaced by some quantity. And this I will use in the following, so thank you for the question. Okay, so now to avoid the 0, there are other ways. And in particular, you can use the celebrated Joffé-Pritchard trap, where there you can play this trick of adding an offset, because the quadrupole you have is just a 2D quadrupole. So these 4 coils are alternatively with current I minus I minus I. And in plane, this produces a quadrupole field like that. So then you're free to add another field in the Z direction which will not shift this quadrupole, but just plug the hole in a sense. And so you can do that with two coils with the same direction of the current, which produce a minimum of magnetic field if you choose the right distance. And locally, you will have a minimum plus a quadratic variation as for any minimum. Okay? And so the total magnetic field, when you compute the modulus, take the square root, etc., at lowest order, it gives you an isotropic trap with a frequency along the axis, which is imposed by this variation, and the transverse frequency, which is imposed by the fact that at the minimum you have the field along x, and when you go away, the field rotates because of the quadrupole taking over with respect to the offset B0. And so this is the way you have this transverse trapping. So the larger this B prime, the faster you go from B0 to this B prime, and the stronger the transverse oscillation frequency. So typically this kind of traps is very nice if you want to have cigar-shaped clouds, because very naturally this frequency will be much lower than the transverse one. Typically a factor of 10 is very common. And then you have a non-zero field at the center. So this is the way the field is. So you see how it rotates when you go away from the axis. Okay, so now that we have a static magnetic field, let's add yet another field, this one, an oscillating magnetic field. And so this is what I call a radio frequency field. It is a magnetic field oscillating at a radio frequency. So now the coupling is the same formula because it's a magnetic field. So I have the static magnetic field plus the radio frequency magnetic field, and I can write the Hamiltonian under the form of some omega 0 Fz. And here you notice that I have taken the radio frequency not in the direction of the static field, but orthogonal to it. And so the fact that you have a field orthogonal to the static field, which allow you to have transitions between the eigenstate of Fz. So this Fx gives you off-diagonal terms in the Fz basis. And there will be resonantly coupling to the eigenstate of Fz if omega has a right frequency, which depends on this value omega 0. So if I now replace Fx by its expression in terms of F plus and minus, and the cosine in exponentials, I can write this Hamiltonian under this form with two different types of terms. This one where e to the minus omega t comes with F plus and its Hermitian conjugate, or the one where e to the minus omega t comes with F minus. And the coupling in front of this term I will call omega plus, and this one omega minus. So if I choose a linear polarization like this one, the omega plus and omega minus are equal, and they are all, both of them equal to omega 1 over 2, the one I've put there. But now if I choose other polarization of the RF field, I can at will change the relative value of this omega plus and omega minus. And so omega plus is the weight on the sigma plus polarization, the one for which the RF field rotates in the same direction that the Larmor precession along the direction of my static field. And for this reason, this one will be resonant within the rotating wave approximation, whereas the other one will be off-resonant with respect to the rotating wave approximation. So essentially, if we stay within rotating wave approximation, this term produces no effect, very, very small effect, smaller by a factor essentially omega squared divided by omega 0. So you have to be in a situation where the coupling is less than the carrier itself. much less than the carrier. And if this is the case, and if the detuning, if the frequency omega is close to omega 0, then we can just ignore this term. And we are left with just this one, for which after a change in the rotating frame, we can write the Hamiltonian under this form, minus delta, where delta is a detuning to the resonant frequency, plus omega plus fx. But this is really nice because this is just the Hamiltonian of a spin. It has exactly the same form of than this one, omega 0 f, not z, but some other u. If I perform a rotation, it will just be some frequency times the projection of f along a new direction. So this is the way I write it there. I can write this expression as some new amplitude times the angular momentum projected along a new direction theta, where the cosine and the sine of theta can be identified to the delta and the omega plus terms. So the cosine is this one, the sine is this one. And the eigenenergies are given by the amplitude, so just that. So now if I perform the same reasoning as before, I have adiabatic potentials, which are just proportional to this amplitude, square root of delta squared plus omega plus squared. So this was at a fixed point, but now if my fields, both the static field and the radio frequency amplitude or detuning, depend on the position, then this is an adiabatic potential which depends on the position. And that's this kind of potential I will describe in the following. No question up to now? No? Okay. So let's take the, yes. Not necessarily. If you change the frequency or the magnetic field with time, or the radio frequency amplitude, then it can. But otherwise, if everything is fixed, then it depends on position only. But you will see that in the following, I will introduce time dependencies. Yes, I have neglected the non-resonant part. I will also come back to that. Okay, so let's consider a very, very simple case where the magnetic field varies just linearly with position, the simplest I can do. So in this case, the detuning, remember, it's the difference between the radio frequency and the local value of the magnetic field, varies linearly with position, because the magnetic field varies linearly with position. So imagine you have a uniform coupling. You end up with a potential like that. And in fact, this potential is very, very similar to the Joffre-Pritchard potential in the transverse direction, where the field varies in direction. And you can see what happens to the atoms in a nice drawing like that. So these are the magnetic states in the bare basis. So the basis, which corresponds to the eigenstate of the static magnetic field, the one which varies linearly with X. So these are the three levels that I would use, for example, for a magnetic trap only. And now I add a radio frequency, which is resonant at this position. So at this position, the local Larmor frequency omega 0 is equal to omega. So this gives me my x0. And what's happening is that when an atom arrives there, at this point the RF is resonant, so it will perform a transition to this state and continue there, where now it climbs a hill, comes back, and oscillates in this potential. And this is a naive description, and if you diagonalize the Hamiltonian, you find these Dre states where there is one trapped state where the minimum is exactly on resonance. So you find a way to trap atoms at positions in space where the radio frequency is resonant with the magnetic field. The radio frequency is the same everywhere, so it means it fixes the magnetic field at which the atoms will be located. So the atoms will be located on isomagnetic surfaces. Okay, So if you have, for example, just to be as simple as possible, a 1/2 spin, then you just have two states. And with position, the eigenstates are like that, and it's just an avoided crossing, these eigenstates. So if we want to estimate the trapping frequency in this direction, we just develop the potential and find that the trapping frequency scales like the magnetic gradient. So alpha is a gradient in units of frequency. And 1/square root of the coupling. And it is exactly the same formula than the trapping for a Joffé-Pritchard trap, where it was B prime at the top and square root of the offset B0, which was along that. So this one plays the role of the offset, and the gradient stays the gradient. So this kind of frequency you can reach. They are large for large gradients and for low RF coupling. So here, be careful. You cannot reduce the coupling as much as you would like, because this coupling also gives you the splitting between the two adiabatic states. So the one which should stay large enough to avoid non-adiabatic losses. Yes? So yes, you have to estimate that, and so this is a difficult point to really estimate the non-adiabatic losses. I will show you this at the end if time allows. Yes. So you can estimate, for example, in Landau-Zener theory, you find that there is an exponential minus coupling squared divided by gradient. So both, but then with it's a bit more complicated with this kind of traps, and we've developed a theory with Barry, but testing with experiment is really tricky. So I will show you experimental results if I can, maybe this afternoon. Okay. Maybe I will split again my lecture and continue in the afternoon. All right. So as I said, what I wanted to finish to say there is that you can reach quite large frequencies in the direction transverse to this isomagnetic surface. So that's why you really have the concept of the isomagnetic surface on which you trap, because this can be between typically 300 hertz and 2 kilohertz. So it's in general the largest frequency of the problem. And then you end up with atoms confined onto the resonance surface defined by Larmor frequency is equal to RF frequency. And what is nice is that this surface you choose. Because if you choose another value of the radio frequency, then you pick another isomagnetic surface. So you can choose this surface, and you can, to answer your question, if you want, vary it in time. If you want to look for collective modes or anything, you can excite like that. So then once we have said that the atoms have to remain on the surface, there can be fine structures inside the surface, because once we have said it is resonant, it will cancel this term. Delta is 0, which what resonance means. So you're left with a potential which is proportional to the local coupling. So now if your local coupling, RF coupling, is not the same everywhere, this can induce some other local potential inside this surface. And indeed, this coupling will not, in general, be the same everywhere, because I said initially, okay, I choose the direction of the RF field orthogonal to the static field. And this gives me, in fact, maximum coupling, because only the omega plus component will couple. Remember, there is a omega plus and there is a omega minus. Now if I change the relative orientation of static field and RF field, maybe my RF field is always the same, but in a quadruple trap, for example, the magnetic field takes any possible direction. And sometimes it can take the same direction with the RF field. And then the coupling will be 0. And so you have to remember that. And so inside the surface, there may be a local minimum, either because omega plus is minimum, or if gravity is present, because gravity will attract the atoms somewhere on this surface. All right. So the first proposal was done by Oliver Zobe and Barry Garway in a seminal paper of 2001. And this is a schematics where you have two magnetic surfaces, two magnetic substates which evolve in a static field, coupled with some RF photon at a given RF frequency. And then if you look into the dressed bases, you find a minimum at the resonance point. So this is essentially the same as the previous slide. So let me now go to examples. For example, if the isomagnetic surfaces are like that, so these ones are the one of a Yoffie-Pritchard trap seen in a transverse, in a plane transverse to the long axis of the cigar. Introducing the RF field will pick a given surface. So now if I change the radio frequency, I will pick another surface. Okay, but this is in a world without any gravity, maybe in the International Space Station. With gravity, you may have a minimum of the potential like that. And this drawing is done with the choice of the radio frequency polarization such that it couples uniformly all around the circle. And this choice corresponds to a sigma plus polarization. So how you do a sigma plus polarization along this direction? Well, you have two RF coils producing fields which oscillate in quadrature like that. And this gives you a rotating RF field in the plane, which corresponds to a sigma plus polarization. So then you just have gravity, which breaks the symmetry. But now if I choose a polarization horizontal perpendicular to the magnetic field, to the main magnetic field, what will happen? Remember, in the Yoffie-Pritchard, you have the magnetic field like that. But if I go there, it turns. But that's the direction I have chosen for my RF field. Okay? So it means that if I make one step right, I will have a minimum for the potential for the omega plus coupling at these points, and that's where the atoms will be attracted. So it's not zero coupling, thanks to the fact that I always have my field along the main direction of the cigar. So even there, it is there. So I still have a component orthogonal to the magnetic, to the RF field, but it's smaller, and so the coupling is smaller, and I have a double well like that. Okay, so let me now go to the second part, where I will give you some examples of adiabatic potentials. So first, I would like to mention a first realization in the 90s already, in the group of Isaac Silvera, and with Bill Phillips as a co-author, Chris Westbrook, Robert Spreeu, and who showed that with a microwave, you could influence the position of the atom and kind of keep them in a microwave cavity. And so the main idea is, again, the fact that you have you should understand this as a potential, okay? And the Rabi coupling, which I call omega, big omega myself, they call little omega r. So here you should read big omega r squared, okay? And so this is the same expression. And in fact, in their experiment, they have a detuning which is more or less always the same because they are in a cavity, and the magnetic field does not vary a lot. But what varies a lot is the amplitude because of the shape of the field inside the cavity. So they have a variation, important variation of the amplitude. Okay, this is a drawing. And here you see cesium atoms which are confined inside the microwave cavity because of dressing of the states with the microwave. Okay, so this is the first ever example. Okay, so let me now describe everything in the RF domain now, because that's where it really developed a lot. So this is the first experimental realization done already 15 years ago in my group. We start from a Yoffie-Pritchard trap at the time. So the isomagnetic lines are like that. And these are atoms confined in the pure magnetic trap, static trap without RF. And now we add an RF field, and you see that the isomagnetic potentials, the selected isomagnetic potential is this one. And because of gravity, the atoms already in this Yoffie trap are a bit below the center. They are a bit below the zero. So when you start and ramp an RF field from a frequency that would be resonant in the center, you nucleate a bubble, if you like, here, that will grow, a bubble of no atoms, and it will push the atoms downwards like that, and that's what you observe here. You clearly see the curvature of the bubble, and this is for a larger value of the RF frequency. So it's very clear, if I draw ellipses on top of that the atoms nicely follow the shape of the isomagnetic bubble. So here it's thermal atoms, so that's why they go quite high. But then we did that with a new setup and a new configuration with condensates. But at the time, okay, this is an even larger temperature where the atoms really fill the bubble. So you can do a bubble on Earth, but with thermal atoms. Okay. So now with the same Yoffie-Pritchard trap plus a transverse RF field, if you are in a situation where the gradient of RF coupling is very large, or which is typically the case on a chip where you have wires, and so the atoms are very close to the wires, there are big gradients everywhere, then you can manage to be in the situation where gravity is not the relevant scale, but more the variation of omega plus, and perform the double well experiment that I explained 2 slides before. And this is the experiment performed by Thorsten Schum and Jörg Schmidt-Meyer, where you control the splitting between the 2 wells in these pictures by changing the RF frequency. So another way would be by increasing the Rabi coupling, so the RF amplitude, at fixed frequency, because also it repels the atoms, its Rabi coupling is larger. So, but this one is done with changing the RF, and then this one is done by increasing the RF coupling. From this kind of double wells, if you relate the atoms, you will get interferometric fringes, matter wave fringes, between the 2 clouds. And this is a setup they used a lot in the past years, in particular to study the phase fluctuations that we can have along these quasi one-dimensional Bose gases. So this is a very nice tool. Another configuration you can reach, always with the IP trap, is to make a ring. So it's not, if you look at this picture, it's a bit misleading, because you have to imagine the trapping more as like a tube than a real ring. So this direction is much larger, in fact, than this one. So this was proposed in the group of Jörg Schmidt-Meyer by Igor Lezanovsky and collaborators. And in principle, you can control by changing the RF polarization between a double well in one direction, a double well in the other one, or a ring. And it has been realized 10 years after in collaboration between a Korean group and Dana Anderson, where you nicely see atoms which are occupying this ring, even if there are still atoms in the center. So the atoms in the center are the one which are in the other spin state, because it's a Yoffie-Pritchard trap. So if you are in a given state, you will be confined to the center of the Yoffie-Pritchard trap, and the other spin state is the one which is confined in the minimum of the adiabatic potential. All right, so now let me consider the dress quadruple trap. So now it's the very simple trap I introduced in the beginning with just two coils with opposite currents. And you couple the spin states with the radio frequency, which means that you will have the atoms confined again at an isomagnetic surface. With the radius, so as you have static fig like that, the isomagnetic surface will be ellipsoids, shrink by a factor of 2 in the vertical direction with respect to the horizontal one because of the divergence of B is 0, so you have a gradient twice as large in Z with respect to X and Y. And the radius of this bubble you tune by changing either the radio frequency or the gradient of the magnetic field. Okay, so you have this kind of isopotential, and the frequencies you get in these traps because of gravity are typically pendulum frequency horizontally and the same formula as before in the vertical direction. So I wrote 1, 2 kilohertz, but it can also be 300 hertz depending on the value of B prime essentially. So as the distance to a center is fixed, you really have a pendulum. So that's why you have square root of G over R essentially, but there are factors because of the curvature. So you are in a situation which can be very interesting to study low-dimensional physics, because the pendulum frequency is quite small, 20 to 50 hertz, whereas this trapping frequency can be quite large, between 300 and 2 kilohertz, 300 hertz and 2 kilohertz. So it's a nice configuration to study two-dimensional physics. And second, you can control many parameters on this bubble. You can control the anisotropy of these 2D gas, because it will be completely rotationally invariant if you choose a polarization for the array field which is circular with respect to the vertical axis. Then the coupling will be maximum at the bottom where the magnetic field is vertical. It will be 0 at the top. So no coupling, Landau-Zener losses, but you don't care because of gravity, the atoms are below. Okay. So you're safe. But now if you choose to use an elliptic polarization or even a linear polarization, you can deform the natural isotropy of this trap and create a direction in which the frequency will be a bit lower and the trap have a main axis. And this you do, for example, if you consider a linear horizontal polarization. As I said, in the quadruple trap, the field takes all the directions. So any choice you will make of the RF polarizations, there will be at least one hole where the coupling is 0, or 2 holes if you have a linear polarization, or anything else than circular will give you 2 holes. So you can start with 1 hole at the top with circular, and then when you change from circular to elliptical, it will split into 2 holes until you reach the linear horizontal polarization where you have 2 holes at the equator, etc. So these holes, as they are a minimum of omega, they attract atoms. So they are attracted towards the 2 holes, and it opens the trap in this direction. And with that, you can control the anisotropy, the in-plane anisotropy of the trap. And you can choose in which direction you make it anisotropic by choosing the RF polarization. So this can be used then to, for example, rotate the trap. And as I said, you can do all that dynamically. So this is an ideal setup for the study of collective modes of the 2D gas, which will be the topic of the lecture of tomorrow. Okay, just a flavor of this kind of modes on this picture. Another thing you can build with these traps if you accept to add light. Okay, this has drawbacks also, but if you superimpose to the bubble 2 sheets of light which you choose blue detuned, so repulsive for the atoms, you can have the atoms confined in between these two, but they also have to be on the bubble. So they have to be at the intersection of a plane and a sphere, and this is a ring. And to load this ring, you switch on the light while the atoms are at the bottom, and there you use your proposition. You add a vertical offset of magnetic field that you increase, and this will just shift the bubble such that the atoms which are stick to a given plane, they will create the ring. So this is the first realization. So that's something we proposed in the PhD thesis of Olivier Morisot, and the first realization was done in the group of Chris Foote in Oxford, where here you see what's happening when you change this DC magnetic field. So in this situation, you have the atoms as a bubble at the bottom of the bubble, and then you shift the magnetic field, and you see the hole created from shifting the position of the bubble. And this is the pictures we have in my group, where it is clear you can change at will the radius of this ring, so either by cutting at different places or by changing the radio frequency. And so here there is nothing in the center, it's just optical imaging. So this is not an atom, these are no atoms, the atoms are here. So in this kind of rings, we observe persistent current, for example. Yes? There was, nobody explained that in previous lectures, no? At least it's on one of the posters outside. I saw that. So how they are made? You have a CCD camera. You have your sample of atoms, and you send a short resonant light pulse. And you make the image of the beam onto the camera, and when atoms scatter light everywhere, there will be less atoms at these positions. So you see the shadow of the atom. So it's absorption imaging. It depends, but this one is in situ, so without time of flight. Okay, so I also mentioned lattices. So imagine you have not just one RF field, but many of them at different values. So each time you cross a RF field, each time it's resonant, you change the internal state, like that. So if you have a linear magnetic field and several values of the RF field, you will change the internal state each time you cross a resonance, and because of that, have an RF lattice. So this drawing was quite naive and early. It should be remade with what we know now better on adiabatic potentials. Up, answer. So this is an experiment by Chris Foote again, a recent paper by Tiffany Harter and colleagues, appeared last year, where they demonstrated two shells, one inside the other, where they even could balance or unbalance the number of atoms in either shell. So this is done with 3 frequencies. This is a resonant frequency. Then another resonant frequency will change, make a local maximum for the spin, and then another resonant frequency, a third one, a new minimum of the spin. So with 3 frequencies, you can have 2 gas on top of each other, and by adjusting one of the RF couplings, you can tune the population imbalance between these 2 waves. Okay, and now if we modulate the field, so introduce time dependence, it opens even richer configurations. And this was proposed by, again, Igor Lizanovsky and Wolfram Kissing. The idea is as follows. So you start with a bubble, for example, the quadruple bubble trap, and which is at this frequency with this coupling. But now you add a vertical homogeneous magnetic field modulated in time at a frequency which is less than the RF coupling. So this is important because the RF couplings gives you what all about adiabaticity. You are not allowed to do things faster than the splitting between states, which is set by the RF coupling. So if you do slow enough, then the atoms will follow the adiabatic state always. But now imagine you have a sphere with atoms which are allowed to go all over the sphere, and you shake it vertically. It will be very unstable for almost all the positions, except one location, which is much more favorable, which is the equator. Because at the equator, it is tangent, so if you move a little bit a sphere along its tangent, essentially it doesn't move. So this is the only stable solution, position, and the atoms will gather at the equator. So by shaking a bubble, you make a ring. So this is called time average adiabatic potentials. And the condition is that you shake slowly as compared to the dressing frequency, the dressing field, amplitude. And the oscillation frequency you should have in your ring should be smaller than the modulation frequency for the atoms to see an average potential. So this is possible to find frequency which satisfy all these inequalities. And it has been demonstrated again in the group of Chris Foote with a very large ring here, 200 micrometers, very smooth. This one is smaller by changing the RF frequency. And it has been also, whoops, I don't have it there, okay. It also has been demonstrated then again by Wolfgang Klisting, who is using that currently to drag atoms, where he has in mind interferometry experiment, and he uses this trap to drag atoms along the trajectory. This is a recent Nature paper. So here it's hot, it's not a condensate. But what Wolf has recently published is you tilt a little bit the ring, so the atoms in fact are located somewhere. There you can make a BEC, and then you play hula up, like that. The atoms will rotate very fast, and he managed to make several turns, and it's still a BEC. And then if you go back to horizontal, it expands, and then it's not clear anymore if it is still a BEC. But okay, it was not the topic of my lecture, so I will probably not show you, but we have done a nice, maybe the last slide of my last lecture, a recent experiment where we rotate the atoms directly in the bubble very, very fast, and the atoms form a nice ring, and they are cold enough to be superfluid and supersonic. But they are not trapped, they are just in the bubble. Okay, and now I come to my last part, so maybe I will do it this afternoon, because it's time. Okay, so I don't remember exactly what is the schedule. Yes, but so let me do that after Carlos' lecture this afternoon, and I will start with the third part directly. Thanks for attention.